All right, so this video is going to be the first video on alkenes. In this video, we're primarily going to talk about just a general overview of alkenes, what the general structure is, how to rank melting points, how to rank stability, and so on. In the next video, we're going to start talking about some reactions. So that's where you'll get into the mechanisms and the products that would happen between a reaction between alkenes and some reagents. And then there's also a corresponding video on alkene practice problems that will follow this video series as well. All right, so what are alkenes? So to talk about alkenes, let's first remind ourselves of the structure of an alkene. And so alkanes are fully saturated, meaning that every single carbon has the maximum number of hydrogens that can be bonded to it because we have no double bonds. Everything is just a single bond. And so if we were to draw in the hydrogens here, you would have 3 on the ends and then 2 for each of the carbons in the middle. However, let's add a double bond here to one of the sides here. And so here, what we did was we added in a double bond. And so to form that double bond, it would mean that we lost hydrogens on the carbons where that double bond formed. And so here we have 1 degree of unsaturation because we have 1 double bond. And so we lost 2 hydrogens. And I can highlight the hydrogens that we lost here in red. Let's say that we were to form 1 more double bond between those other 2 carbons on the end. Now we end up with 2 hydrogens on each end and then 1 for each of the ones in the middle. And so now we have, we have 2 double bonds here. So this is still a special case of alkenes called dienes, which we'll get to in a little bit more detail a bit later. But here we have 2 degrees of unsaturation and 2 double bonds in the entire structure. And one thing I want to note about alkenes is that here in the structure that I just drew out, we have 2 that are right next to each other. And I'll redraw it right here. And we can see that they're spaced apart by a single bond. We very, very rarely see a structure like this in organic chemistry, where we have a single carbon and on both sides we have alkenes. And so if you're drawing this, I would suggest, especially in this chapter, I would suggest double checking your work and making sure that you don't have this structure. Again, usually you have that single bond between adjacent alkenes. Another thing I want to point out here is that this structure right here, which is a really, really common structure in organic chemistry, where we have a ring with 3 double bonds in the ring, this does not fall into the category of reactions that are covered in this chapter, even though it has those double bonds. And so if you see this ring structure, just ignore it for the purpose of the reactions. It will not undergo the same reactions that most alkenes will undergo. And later in this course, you will talk about different sets of reactions that this structure would undergo. But for now, for this chapter, just ignore it. Do not use those double bonds within that ring to do any of these reactions. And so we ignore it. However, one thing that you don't want to ignore is a structure like this, where you have just 2 double bonds in a ring, or maybe 1 double bond. This ring is not complete for that double bond system in the middle because you don't have a double bond here on the left. And so this structure will undergo reactions. And I just want to point that out now just because a lot of people end up accidentally reacting that top reagent and making mistakes with that. All right, so a few things that we need to talk about in relationship to alkenes is first their structure. So let's say that we have this structure right here, where we have a methyl group on one side. And so I'll draw in the hydrogens here for simplicity. And then we have an OH on the other carbon here. And so here we can see that both the OH and the methyl are currently drawn above the plane of that alkene. So if we were to draw a straight line through that alkene, we can see that the OH and the methyl group are on the same side. And so let's draw the other one where we flop the position of that OH. And so we still have that methyl group pointed up, but now that OH is pointed down. And so now if we were to highlight those groups, we can see that they're on opposite sides of that plane. So if we draw that straight line through, we can see that the OH and the methyl are on opposite sides. And so these two structures are not the same because we don't have free rotation around double bonds. So around single bonds we do, but around double bonds we can't rotate around and make those compounds the same. And so I'm going to put a not equal sign here to show that these two structures are not the same. They will form different products in different reactions. And so it's important to make sure that you're not treating them the same way. And again, the reason for that is because we don't have free rotation around double bonds in the same way that we do around single bonds. And so to differentiate between these two structures, we use cis and trans terminology. And so this one is going to be cis because those groups are on the same side of the double bond. And this one is going to be considered trans because those two groups are on opposite sides of the bond. And so for this, it's the cis and trans works. However, cis and trans really only works if we have H's because those H's are small and we kind of don't really care about them. And so to differentiate between different types of alkenes where we have more substituents instead of H's, we use E and Z terminology. And so in the case of the cis, we end up calling it a Z isomer. And for trans, we call that an E isomer. And so for your nomenclature unit, you might have to use Z and E to differentiate between those alkenes. And so let's go into a little bit more detail about Z versus E designations. Because a lot of courses will ask you to name or to draw a alkene given its Z or E designation. And so I'll just go through a few quick examples of what those look like. So let's just redraw those ones that we just drew in. And then what I'm going to do is add in a few more examples here. So we'll do this structure right here, where we take that first structure, but then add a methyl group to that bottom or right carbon. And then we'll do a more complicated example here. Where we have 4 substituents on that alkene. And so for this first one, we have these 2 groups are on the same side. And so since they're on the same side, we use the Z term. And the Z comes from a German word that means same side. So that's where the Z isomer part comes from. Here we can see that we have these 2 groups on opposite sides. And so this will be the E isomer. And so it's similar to trans in that it's the groups are on the opposite side of the alkene. All right, so now we got to this third one. And so here this is going to be a little bit more complicated because now we have multiple substituents on some of the carbons. And so for each carbon, we have to determine which substituent will take priority. And so let's start with the one that I just highlighted or circled in red. And so on this carbon, we have 2 substituents. We have that methyl group going to the left and up, and then we have that hydrogen going down. And so for priorities, we use the same priorities that we did for R and S. And so a methyl group would take priority here. And so we can highlight that. On this right carbon that I just highlighted in green, we have this OH and then a methyl group. And so based off the priorities that we talked about previously, that OH would take priority. And so we would want to highlight that one. And so now we only compare the relative orientation of those 2 groups. And so we can see that those 2 groups are on the same side. And so this is going to be a Z isomer because those 2 highlighted groups are going the same direction. Next, we can do that last one. So again, we're going to start off with this red carbon that I just drew a dot over. And so we're comparing this O methoxy group and a methyl group. And so for these, we know that the oxygen takes priority. And so the group that we will use for E versus Z designation will be that one. For this right carbon here that I just highlighted in green, we have this long carbon chain or a methyl group. And so we know that that bigger carbon chain is going to be the priority. And so we'll keep that as our highlighted group that we will use to determine the Z versus E isomer. And so here we can see that they're on the same side. And so this is going to also be a Z isomer. And then for alkene practice problems, there's a few more complicated structures over here that you can take a look at if you're not want to practice. All right, so that's for nomenclature. Next, what we should talk about is the stabilities of different alkenes. And so stability of alkenes is determined by two primary things. And I should mention that this is for alkenes that are approximately the same size. Obviously, once you get like much bigger structures, there's going to be other things that matter. But for now, we're just comparing the alkenes of similar size. And so here we're going to care about the number of substituents, so the number of carbon chains or other groups that are bonded to each alkene. And the other thing that we're going to care about is cis versus trans for alkenes that have multiple substituents. And so let's start off with a simple alkene with no hydrogens attached to it. We just have a simple two carbon alkene with two hydrogens on each carbon. We have no carbons attached to it at all. Next, we can draw the one that's going to be more stable. And so as we add in methyl groups, so we're going to substitute out one of those hydrogens for a methyl group, we end up forming a more stable alkene because now we have one substituent. All right, next we're going to add in another methyl group. And so here we have two options. We could either add in a methyl group that is on the same side as the one that we already had, or we can add in one on the opposite side. And so we can get the cis versus trans groups here. So both of these in the middle have two substituents. We have two methyl groups. And this trans isomer is more stable than the cis isomer. All right, last we can add in those, that third substituent or methyl group. And then lastly, we would just have a fully substituted alkene where we have carbons on all the sides and no hydrogens. And so that one will be the most stable. All right, so that's basically the only thing that really matters for alkene or for ranking stability of alkenes that have carbons attached to them. That's the primary. These are the two primary factors that will contribute to them. And there's a practice problem for ranking stability here, so you can practice that on your own time and watch the solution video. All right, so the next thing that I want to talk about is the cis versus trans dipoles. And so for this, I'm going to draw out a alkene substituted with two methyl groups here, and then the other one, which would have them on the same side. So here we have trans and cis. And so what we can do for both of these, I'm actually going to make both of these a bit bigger, is we can draw in the net dipoles the dipoles that we get for each of these groups. So alkenes are electron rich. And so we'll talk a little bit more about that in a second, but we know that there's a lot of electron density within that alkene. And so if we were to draw in the dipoles, it would look something like this. And that's because this methyl group, or CH3 group, is weakly electron donating. And so we have a very weak dipole here like that. Um, in the case of the other group, we also have this dipole here. And then we can draw those in on the right structure on the right as well. And so each of those methyl groups independently has a small dipole. And so if we think about the net dipole, and I'll use purple, or actually I'll use green to show the net dipole. We get a small net dipole in the case of the structure on the right, because those dipoles don't cancel each other out. Meanwhile, the trans alkene has no net dipole because those two cancel each other out. They're in opposite directions of each other. Their directions cancel out. And so because this structure on the right has a small net dipole, this contributes to a higher BP and melting point due to intermolecular forces that would exist in a solution containing a cis alkene. And so having a cis structure contributes to a higher melting point than that trans one does. And this is relevant for things like when we think about like oils or lipids that are found within cells for a lot of different things that can affect the melting point of those different compounds. All right. So the last thing that I want to talk about with alkenes is nucleophilicity, or the alkenes as a nucleophile, and why they can act as a nucleophile within different reactions. And so for this, let's draw out a alkene. And I'm going to draw this big so we can draw out the different types of bonds that we have. All right, so we know that an alkene has two different types of bonds. We have a sigma bond and a pi bond. And so if we were to draw these out, we know that the sigma bond looks something like this, where it's kind of like close to the middle of those two carbons. Now I'll highlight the sigma bond in red over here. And we also know that that pi bond looks something like this, where the structure of it extends above and below that alkene. And that we kind of get electron smearing between these lobes. And so this pi bond extends above and below the alkene. And so it's further away from the center of that carbon-carbon bond. And so as a result of that, it is weaker than that sigma bond. And the electrons in it are available for reactions. And so within reactions of alkenes, these electrons can act as a nucleophile from that pi bond. And I'm going to write that out as a separate sentence here. Just because a lot of tests like to ask like what electrons are involved in the reactions between alkenes and something, and it's the ones that are found in the pi bond. And so they're available for a reaction or to form a bond with something. So overall, the alkene acts as a nucleophile because it's donating those electrons. And just as a reminder, nucleophiles want to give away electrons, electrophiles want electrons. All right, and so in all of the classes of reactions that we'll talk about next, we'll have that alkene acting as a nucleophile. All right, so in the next video, we'll get into hydrohalogenation. In that one, I'll link it below.